Welcome. This module is for understanding what is input offset voltage, alright, and then another point is slew rate. Two things we will see in this particular module. Again, these are the characteristics of an operational amplifier. These are the set of experiments that I am covering as a part of this particular course, which we have already seen in theory part. So, this is the theory part. We learn what are the things: input offset voltage, input offset current, slew rate, and then we have seen CMRR, we have also seen inverting amplifier, non inverting amplifier, oscillators, and so on and so forth. Here we are actually testing it by making the circuit, right, and that will help you. I hope that will help you to understand how you can use the operational amplifier and how you can find different parameters. So, with that, let us see what you mean by input offset voltage. Now, assume that you have given no voltage at input terminal, or the input terminals of amps are grounded. That means inverting terminal is ground, non inverting terminal is ground. So, what you expect at output? What do you expect at output? Output should be 0, right. But when you actually measure the operation amplifier by testing this particular experiment, that is, you give inverting terminal ground, non inverting terminal ground, and you measure the output voltage, what you will find is, you will find that the output voltage is not 0. So, if the output voltage is not 0, how we can make it 0, right, and the voltage required at the input to make output voltage 0 is your offset voltage. This is what offset voltage means. Now, let us see on the screen what the definition is and how we can measure the output offset voltage, alright. So, what we have seen, when both the input terminals are grounded, right, that means I take a operation amplifier and I ground both the input terminals. Now, this is just an example, okay. We will see example in the next slide, circuit in the next slide. Just I am showing. So, when the input terminals are grounded, ideally the output voltage should be 0, right, but in case of practical operation amplifier, a non-zero output voltage is present, right, and to make this output voltage 0, a small voltage in millivolts, a small voltage in millivolts is required to be applied to one of the input terminals, alright. So, this small voltage which is required to make the output voltage 0, right, this small voltage that is required to make the output voltage 0 is called the input offset voltage, and it is denoted by VIOS, alright. Easy to understand what is input offset voltage, but how to calculate it, right, how to calculate it. So, let us see input offset voltage experiment. So, if I want to measure the input offset voltage, now you see here there is a mu A741, we have used resistors, right, same value of resistors or 100, here is 100k, right, and plus VCC minus VCC, VO, we have to measure the value of voltage VO. So, in what we are assuming that input we have grounded, means output voltage should be 0 volt, right. Let me write it down here. So, output voltage would be 0 volt when inputs are grounded, right. This is what we think. So, if you want to understand whether output voltage is 0 or not and how much voltage we have to give at the output, then you have to connect the circuit like this. Now, let us see, connect the circuit as shown in figure, it is very easy, right, and I am sharing these slides with you. So, you can do it anywhere. Connect the circuit as shown in figure. Now, measure the DC output voltage at pin 6, this is pin 6, we know, right, using multimeter. You can use multimeter, you know how to use multimeter now, and record the result in table. Where is the table? Table is here, this is a table. Calculate input offset voltage and record the value in table, so easy, right. So, V out, whatever V out is there, we will write it here, right. We can measure V in by this formula, whatever V out we get divide by 1000. Why? Because of the ratio, alright. So, let us see this actually in the experiment. We will connect, we will take our operation amplifier, 3 resistors of this value, we will connect it, and let us see the output voltage initially, and then we understand that we will not see this output voltage 0 volt in practical op amp, we will see some millivolts, alright. So, let us see this experiment. So, again we can see on the breadboard which is right over here, right. So, can you please come? Yeah. So, those who cannot know whom I am calling Sitaram once again. So, he is involved with this experiment, he is helping us to understand how the circuits are connected, right. So, there is a breadboard, as you see here there is a breadboard, 3 resistors, right, and then we have the indicator circuit, we have given the bias voltage plus 15 minus 15 through the DC power supply, right. Now, we are measuring the output voltage. So, both the input voltages are ground, both the terminals are grounded. Okay. So, now we are understanding the output voltage. From where output voltage we can measure? We can measure the output voltage at pin number 6 or between pin number 6 and ground. So, what is output voltage? Let us see. Again the multimeter is in DC, DC. So, he is connecting the positive to 6 and the another terminal to ground. What we see, there is some output voltage, you can see 7.6 millivolts, 7.6 millivolts. Now, what should be the actual thing? Actual thing is the output voltage should be 0, right, but in actual op amp, in the practical op amp, we are not able to get the value output voltage 0, right. Thus, we can, if we get the 7.6 millivolts, right, whatever we have obtained using the multimeter, if I put the same value in the table which is on the screen, right, then I can write 7.6 divided by 100, right, that will be my Vin. That means this much voltage at the input I have to apply to make my output 0, easy, right. So, now you can do these experiments at home. What experiment? Input bias current, input offset current, input offset voltage, right. Now, let us see the another characteristics of an operation amplifier, which is the slew rate, very important characteristics of the operation amplifier. Let us see slew rate, right. So, what is slew rate? So, given on the screen, what is slew rate? Maximum rate of change of the output voltage in response to a step input voltage, right, maximum rate of change of output voltage. So, if I apply a step input voltage which you see here, what is the change in the output voltage? What is the change in the output voltage, right, maximum change. Now, measure of how fast the output can follow the input signal, this is also the slew rate, alright. It can help us to understand how fast the output can follow the input signal. So, when I give an input signal, how fast I get the output, right, that is a measure of slew rate. That means, if you see in this particular graph, what we see, there is a x axis is your time in microseconds, y axis is voltage, right. This I have taken from Robert Boylston, electronic devices and circuit theory, this particular graph, just to help you understand what exactly this means. Means that you can refer to this book as well, right, you can refer to this book and you will get in detail what exactly the slew rate means. But let us understand from this lecture what this graph means. Graph is very easy, there is a input voltage shown in blue color here, right, and then this output voltage is shown in red color, right. So, everything is red because my pen is red. So, just not to confuse you, now you can see in this particular graph there is a blue and red signal, right. So, how fast your output, that is your red, follows your blue, that is your slew rate, very easy to understand, is not it. So, slew rate is also given by delta V out upon delta T, change in the time, delta V out is change in voltage, where delta V out is nothing but plus V max minus V max. So, plus V max minus V max, this difference of this, right, is your delta V out. We can see here in this particular formula, right, that V out, delta V out equals to plus V max minus V max. We can also see in this slew rate, the formula is not not visible completely. So, just ignoring this one, I will write here delta t, alright, delta V out by delta t. This is slew rate. Now, in reality, if we want to measure slew rate, right, that means experimentally we want to measure slew rate, what we can do, what kind of circuit we can have. So, let us see this circuit. Now, you can see the screen again, right. In the screen what you see, there is a mu 741, right, and you have applied voltage at the non inverting terminal 1 volt peak to peak. So, what are the steps? First step is connect the circuit as shown in figure. So, again these slides are with you, you try to do at wherever place you have the access to work on this, right. Laboratory, you can use at laboratory, home you can work at home, wherever you are comfortable. Again always understand how to operate any system, right. Safety is first. So, if you do not know how to use it, do not try it at home, is same thing, right. Even simple things do not try until you know, right. So, be cautious when you use anything, right, because finally we are applying DC voltage, we are applying voltage, we are using the equipment. So, we should always be careful, but the point is if you want to measure slew rate, follow these steps and you will be able to measure the slew rate. How? So, first is connect the circuit as shown in figure, use function generator. Now, function generator we have seen how function generator is used, right, and we can apply 1 volt peak to peak square wave. So, we will see in the experiment how we are applying 1 volt peak to peak square wave at a frequency of 25 kilohertz. Let us keep frequency of 25 kilohertz, alright. So, now we need another system which is oscilloscope. So, it may not be possible for you guys to have everything at home, otherwise people will get angry on you. So, do not do experiments which are really costly or which consumes lot of space in your home. Okay. So, try to go to your laboratory or you can access your friend's lab, right. You can take permission from a teacher, and I am sure that anyone who is there to help a student will give you an access to the laboratory where you can do this simple experiments, right. So, with an oscilloscope observe the output of operational amplifier. You can see we will see an oscilloscope and we will observe the output of operational amplifier. We will measure the voltage change delta V with respect to delta T, right. Why? Because we have seen in the last slide the formula for slew rate is nothing but delta V out upon delta T, is not it, this one, delta V out upon delta T. So, what we are measuring? We are measuring the fourth point, which is this one, measure the voltage delta V and time change delta T of output waveform and record the results and calculate the slew rate, alright. First step, let us repeat, connect the circuit. Second, apply 1 volt peak to peak at 25 kilohertz using function generator. Third, with an oscilloscope observe the output waveform. What we have to measure? We have to measure the change in delta V, change in voltage at time delta T of the output waveform, and from that we can measure the slew rate SR, which is given by delta V by delta T. Using the circuit, set analog function generator to 1 kilohertz. Now, using the circuit, adjust the signal level 20 volts peak to peak, increase the frequency and watch the frequency somewhere about 10 kilohertz, slew rate distortion will become evident. So, this is this particular things here which is written, this is not written in the table, it is not in the table, right, but this is just to understand what is the maximum frequency that our operational amplifier can operate at. To know that, we will, if we keep on increasing the frequency, if we keep on increasing the frequency, right, we will see that somewhere the slew rate, right, distortion will become. So, there will be some distortion in the slew rate. At this distortion, right, we can say that the maximum frequency at which the op amp can be operated is called bandwidth, and we can also measure this value in table. Here we are not measuring the slew rates, that is why if you do not see a separate we are not measuring the maximum frequency. So, that is why we are not looking at the table or a column in the table to measure the frequency, alright. We here our idea is just to measure the slew rate, and for measuring the slew rate what we have to measure? Delta V and delta T. What we need? We need a frequency generator, we need a oscillator, we need a oscilloscope, and we need a operational amplifier. So, let us see how we can do it. The same circuit I will show it to you on the breadboard, and then we will see how it looks like. So, let us see on the breadboard, like I said a little bit while ago. you see the breadboard here, and the circuit is similar to what we have seen in the screen, and there is a operation amplifier. We have connected this operation amplifier to the function generator. This is a function generator like you can see here. So, I will ask again Sitaram to come here and connect it. So, that I will change the voltage, change the frequency, so that we can understand how this slew rate can be measured. Okay. So, Sitaram, can you please come here? Yeah. Alright. So, what we have done here is we have connected the frequency generator to the operation amplifier. So, the signals are here, which is holding the probe. This probe is connected to the frequency generator. If you closely see as a frequency generator, you can see that we have applied 25 kilohertz, right. You can see in the screen 25 kilohertz, correct. Now, this is a square wave that we have applied. You can see square wave here somewhere here, right, and this is 25 kilohertz. Now, this when you apply this 25 kilohertz, the high level is 500 millivolts. So, 500 millivolts. Now, you have to understand what is the output voltage and what is the time, what is changing the output voltage, what is changing the time. That you can do by taking help of the oscilloscope. So, oscilloscope is right here, and here you can see the output voltage, right, and the change in output voltage with respect to time. So, yes, now we can see, right. So, we can see the signals which we were able to look at the on the screen. Similar signal we can see here. We are applying the input voltage and there is some lag in the output voltage. This lag in the output voltage we can see using the oscilloscope. Alright. So, now if we know what is the change in the voltage, that we can understand using oscilloscope, right, and then we see this what is the change in time, that is delta t. So, delta b v by delta t will give us the slew rate. So, it is very easy. Again you see here we are constantly applying plus 15 minus 15 to the operation amplifier. We are giving a particular frequency, that is 25 kilohertz through function generator, and we are measuring the output voltage using the oscilloscope. So, we require this all three things together along with the operation amplifier to understand this slew rate. What slew rate is a change in the voltage, output voltage, right, divided by delta t. So, delta v by delta t. Now, one thing if you remember in the slide we have said that increasing the frequency and watch waveform somewhere about 10 kilohertz, slew rate distortion will become evident. So, let us do that experiment. Let us bring the frequency low and let us increase it slowly, and you will see on the oscilloscope the change. Alright, can you please do that? Yeah. So, when he is going to change the frequency using frequency generator, you can see the oscilloscope here, and you can see here the distortion will start occurring, or slew rate will start changing, right. So, he is changing from almost 220 to 35 hertz, right, 235 hertz, and he is changing. So, guys, you focus on this oscilloscope, all right. Now, you see here he is changing the frequency, right, he is changing 365, 375, you focus on here, what happens? See, he is increasing it 425 kilohertz, 465 kilohertz, you see there is lot of distortion, right. But if he goes on decreasing the frequency, can you decrease it again? Yeah. If you see that he is decreasing the frequency, the distortion becomes less, and it is easy to understand or easy to measure the slew rate. So, this is how we can understand. So, from that what we also understand, that at a particular frequency the op-amp cannot be operated, that is the maximum frequency at which the operation amplifier can be operated. So, there is a two way or easier way to understand at what frequency operation amplifier can be operated. At frequency, well, the slew rate will be distorted, right, or can we measure the slew rate? Yes, when we apply input signal, you can see there is an input signal, right, which is yellow, you can see blue color or greenish color or light blue, that is your output signal. There is a lag between input and output. This change in delta t and change in delta v is your two values that you have to measure. When you measure these two values, if you come back to the screen and you will see that if you put this values, you substitute this value onto the table delta V and delta T, you are able to measure the slew rate. So, for this particular module we understood what exactly slew rate is. We have seen an experiment how we can measure the slew rate. Okay. So, this is the end of this particular module. I thank you. One thing that you can see on this last slide also, and every time I will try to bring one quote from some famous guy who has done something good in his life, right, either in terms of science or in terms of engineering or in terms of academics or in terms of society, anything, a person who has done something on which we can also try to follow. So, you may be knowing this scientist Thomas Alva Edison, and he said that our greatest weakness lies in giving up. The most certain way of to succeed is always to try just one more time. That means that we generally try to give up the things, right, when it does not work. Suppose you work on this experiment what I have taught you, and you will see there is no signal, and you said, oh, this is not working. Do not do that. Try once again, try once again, you will succeed. That is what he also said, that the most certain way to succeed is to try one more time. So, do not give up, try to see, try to understand the series, try to understand what experiments we have done, try to understand the characteristics of the operational amplifier, and I am sure that you will understand more when you do it by yourself. Alright. So, always try to learn and then perform the experiments by yourself. Once you perform experiments by yourself, you will have more idea or more questions or more difficulties that you can ask to me or try to solve by yourself. Alright. So, this is the end of this particular module, and I will see you in the next module with more experiments. Bye.